Hey guys, this is example 29.6 out of the textbook. What we basically have here is a rectangular current conducting plate. This is hollow, kind of like that. But basically what's going on here is this is connected to a hinge right about here along this side A. And it's able to freely rotate kind of like that. So it also has a current running through it in a counterclockwise direction and an electric field moving up. So because of the right-hand rule, we know that the current's going this way and bending towards the electric field, it'll be pointing out this way. So this is a side view, or actually an underneath view of this side B here of this rectangular plate with the the resultant force pushing out this way. Now what's also going on is, because this is kind of hard to see, but as it's rotating there's a gravitational force pulling it down this way. But the torque force of the velocity of the resultant force pushing it back this way is causing it to kind of add to the gravitational force as it's going on. So we have two different forces of torque counteracting that, kind of adding together to a total torque force. So what we can do is take a look at this beam as it's split up into two different parts here. We labeled this part as B over 2. This is angle theta. And then we have this part of the triangle as B over 2 cosine theta, and this is B over 2 sine theta. And again, this is the electric field moving up this way. So what we're first going to want to do is look at the torque of the electric field, which is equal to mu, the resultant force, times the the magnetic field. And we know that mu is equal to the current times the area across B. And we already established that this is the k hat direction, so it'll be across B, k hat. And because we want to specifically look at it as it's tilted, we want to look at this length right here and how far it's tilting. We want to look at the cosine theta length of B. So we'll put cosine theta to chop this up into the area where it's just pointing up, down that way. So this is actually going to be negative because it's pushing in the opposite direction. And we know that the area of this rectangle is going to be A times B. That's the electric field, cosine theta, k hat. So what we're going to want to do next is look at the torque for the gravitational energy pushing down this way, which is just going to be radius, or there's not a radius because it's a rectangle, but the length times across mass times gravity. And we know this radial length, I guess, that it's turning to be B over 2 sine theta. And then mass times gravity. So we just have that established right there. And this is in the k hat direction. So then what we can do is come all the way over here and add these together because they both equal 0. So we have, which is equal to 0, minus I A B cosine theta k hat plus b over 2 sine, hope you can read my writing, theta mg k hat. We'll move this guy over to the other side. IAB b cosine theta k hat is equal to b over 2 sine theta mg k hat. Then what we'll want to do at this point is take a look about how we can simplify this with cosine and sine. You know that sine over cosine is tangent, so what we can actually do is bring this stuff over here. So we have I, A, B, big B, over B over 2, mg is equal to sine theta over cosine theta, which we know to be tangent theta. So we got that simplified right here. Then all we need to do is take a look about how we can simplify this right here. These b's cancel out like that. This 2 will get put up here. So it becomes 2I A B over mg, which is equal to tangent theta. Then all we need to do is take the inverse tangent. Theta is equal to arctan 2I A B over mg. That's it, folks.